Hello, fellow people. So, welcome back to my series on building data structures in C. And today we're going to be working on a binary search tree. So, in the previous video I released, I was working on this HTTP request structure. And with it, I needed to parse out these header fields into key value pairs. And in order to do that, I actually need a data structure called a dictionary. But the basis for my dictionary is going to be this binary search tree. So that's why we're going to be building this today. And before I get into that, I want to show you a conversation I had with a person on Reddit. This is our good friend Tim36272. And he was commenting on my implementation of the node object in the linked list. And what he pointed out was that I could, instead of using an enumeration for different data types, I could just pass in the size of the data and the data itself and just put that directly into my void pointer. And I thought this was a great idea, so I'm going to implement that today first. I will put a link to this conversation I had with Tim in the description so you can go and sing his praise to him. Anyway, we're going to implement that first. So let's go to our node object. And basically what he's talking about is right here. I pass in the data type, which is a reference to this enumeration. And with that data type, I use a switch statement to determine what should be done. But in fact, I can delete this whole switch statement. And if I simply include the library string.h, then I can say node.data equals malloc size. And now instead of size being an integer value referring to the number of elements in an array, it's going to refer to the actual size of the item in bytes. And then I can just use this function memcopy. So I can say memcopy. And this is the destination, so node.data. And then the source is going to be data, and then the size is going to be size. And that can replace that entire switch statement, and now I have no need for this data types enumeration, which is great. But I need to do a little work here. So first I need to remove data types from the struct. So let's get rid of that. I also no longer need to store the size of the data. And in my constructor, I need to take out this. So all references to the data type need to go. So right here it can go. And then right here that can go. That can go. Let's see. And then in linked list as well, I need to remove all instances of data type. So that should be good there. Take out this one here. We're going to leave that for a second. Okay, up here. Did I do too many there? No, I didn't. There it is again. Here we go. Thank you for pointing that out to me, Xcode. That makes my life easier. Okay, that should be everything except maybe in Q. Yeah. Get rid of that. And let's get rid of that. Okay, that should be everything, if I'm not mistaken. Yeah, so that makes our node function a lot simpler. Okay. So that was thanks to our friend Tim36272. So thank you, Tim. That was fantastic advice. And I had a much longer conversation with him about a lot of other things. So if you're interested, you can go and read that. Again, link in the description. So today we're going to be building a binary search tree. And let's first look at a little bit of the theory behind the binary search tree. So here is an article from Geeks for Geeks. I will put a link to this in the description as well. And here is an example of a binary tree. And there's a difference between a binary tree and a binary search tree. A binary tree refers to a tree. It'll have a single parent node. We'll call it the head. It has a single head node. and each node will have no more than 2 children. As you can see here, you can have nodes with no children, or as you can see here, you can have nodes with 1 child, but no more than 2. And generally speaking, you're aiming for 2 nodes per child. So here you have 2 nodes, here you have 2 nodes, etc., etc. Now that's a binary tree. And a binary search tree is a particular kind of binary tree. So the binary search tree is one in which these numbers follow a specific pattern. So we start with our head node, and everything to the left of any given node is going to have a value less than its parent, and anything to the right is going to have a value greater than its parent. So you can see here, let's say we want to insert the number 7, or find the number 7 in the binary search tree. We have 8 as the head, and 7 is less than 8, so we move to the left. And here we have 3. 7 is greater than 3, so we move to the right. We have 6. 7 is greater than 6, so here is 7. And the benefit of this is that it is a really efficient way to store items, and that it's efficient in terms of searchability. If I want to find a particular number in this, let's say I'm looking for this 13, I can start with my head node, and I can say 13 is greater than 8, and with that one comparison alone, I can eliminate half of the tree. And assuming that every single node has 2 children, every comparison you do will reduce the number of remaining children in half. So in big O notation, this is a log n function. It will have a limit for how long it takes. So for example, if there are 1 billion nodes in this tree, it will take roughly 30 iterations to find it. Let's demonstrate that. So let's pull up this Google calculator, and we're going to start with 1,000, 1 million, 1 billion. Okay, set that equals. We're going to take our answer and divide it by 2. So every time we do this, we are essentially cutting out half of the remaining tree. So if I hit this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. So you can see that within 30 iterations, I have managed to bring the number of nodes I have to look at to less than 1. So if there are 1 billion nodes in my tree, I can find the node I'm looking for within 30 iterations. And that's only assuming that it is way down there in the list. If it's higher than that, it'll take less than that. So generally speaking, it will take no more than 30. And in this case, I had to be specific with when I say generally speaking. So let's say you have an array, and your array is sorted, and you use a binary search on that. This number is going to be a lot more accurate. In the binary search tree, as you can see with this line here, you can have instances where it's just a line of items, and this half of the tree is just a linked list, and you're essentially doing a sequential search on this linked list. But hopefully your tree does not do this very much, so it is roughly a binary search. It's an efficient way to implement a binary search. Okay, so that's the basic theory. Let's go into actually building it. I want to reuse my node, and in order to do that, I'm going to need to make a slight modification to it. So we can see here that this is the linked list, this 8, 10, 14, 13, and this arrow would represent our pointer to next. But we also need a pointer to previous. So I can just add that in. So I can say struct node previous. And then in my node constructor, I can say node.previous equals null. And this will have pretty much no effect on my linked list implementation, but will allow me to use the binary functionality of the binary search tree. So let's create a new folder for trees. One moment, it seems that there is already a file in there. I need to delete this. I was experimenting earlier. You're seeing a little behind the scenes here. Okay, so let's call this trees. Okay, now I have my node object, and my node object applies to a linked list, but I'm also going to be using it in the tree. So I want to create another folder, and I want to move my node. So not a file, cancel that, new group, and I'm going to call this common. And I'm going to put my node in here, and I'm going to, in my linked list, say .. common / node. And I don't think I need to put that anywhere else. Nothing else imports node directly. So this folder, it just makes it clear that the node does not belong directly to list objects. This node is used for all kinds of objects. So now let's create our tree. So I'm going to create a file. I'm going to call it binary search tree. Okay, so let's start with our header file. We can get rid of that, and we can include .. That symbol just goes back a folder, and so I can say common / node.h. Okay, so we're going to define a structure for our binary search tree. So struct, and let's do our struct def, binary search tree, and our fields. So here we are again going to have a head, just like our linked list had a head that pointed to the first item in the list, if we can think of that as our linked list. Our head is just going to be this top level node. So we're going to have a struct node pointer called head. And here's where things get a bit tricky. If you remember in my node, I don't force the user to use any particular kind of data type. So in order to do things in the binary search tree, we need a way to compare these functions to one another. But since I don't know what sorts of data are being stored, I need the user to actually specify a compare function. Now this compare function is not something I really want them to just use, but I have to declare it as a public member variable. That way they can define it themselves. So we are going to have a compare function. And this compare function is going to return an int. The reason for that is they can pass in whatever data they want, and it will return -1 if the first one is greater, it'll turn in 1 if the second one is greater, or it will return 0 if they are equivalent. So we'll call this int compare, and they're going to pass it two things. Well, two void pointers. Void pointer data1 and void pointer data2. And this needs to be a function pointer. Okay, and the reason I have them passing in two void pointers is that I need this compare function to apply to anything that they're doing, whether they are comparing strings and integers or just two integers or whatever. So that's where the void pointer comes in. And I don't want them to be thinking about nodes at all. So they're just going to pass in data. All right, so they're going to be able to define their compare function, and then the functions I actually want them to use are a search and insert function. And the search function is going to return the data. So it'll return a void pointer, and we're going to call this a function pointer called search. And this is going to take a void pointer to the data they want. But before that, we also need to pass in the binary search tree itself. That way we can retrieve the head. And again, this is like using self in a Python application. So we will say struct binary search tree pointer tree. I don't know if you can hear my neighbor playing music outside, but that's quite inconsiderate of them. Anyway, okay, so we pass them that. And then we're going to have our insert function. And this won't return anything, so we'll just say void, another function pointer called insert. And we're going to pass it struct binary search tree pointer tree and void pointer data. So this one inserts data and the other one finds the data. And then we're going to want a constructor for this. So struct binary search tree. What is it not like there? It wants that. It's going to return a binary search tree, and we're going to call it binary search tree constructor. And we are going to have to pass this the definition of our compare function. So we'll pass it int compare with these points. Okay. Now, I'm not actually going to implement a compare function here. The user is going to define their own compare function, and they're going to pass that into their binary search tree. That way it can accommodate whatever data they want, and they can make their comparisons as complicated as they need. Off camera, I might actually define a few standard ones. So if you're comparing integers, for example, we'll do that. But I am not actually defining the compare function for them here. So we're going to work in the .c file, and I'm actually going to implement the search and insert functions. So let's open up the header file next door. Okay. So we're going to have struct binary search tree constructor. We're going to pass it those. And here's our definition. What is it not like there? That's fine. Is it fine? I think I need another one. Yeah. Okay. What now? Okay. So what do you want? Conflicting types. You know what? Let's just copy and paste the whole thing. Didn't like something. I don't know what it did wrong. Okay. And we're going to first define a new instance of the binary search tree. So struct binary search tree. And at the end, we will return tree. And in between, all we need to really do is say tree.compare equals compare. And that's the whole constructor. So the user will define their function elsewhere and just insert it in here. Now come a few tricky ones. So first I want to basically replicate some of the functions from my linked list. So we can see I have this create and destroy node. Again, I don't want the user to actually be working with nodes themselves. This whole interface should do that for them. So I'm going to have to copy and paste my create and destroy node functions here. So let's just do that. And I'm going to double check these to make sure that they are not doing anything strange. That seems fine. Yeah, that's all good. And destroy, yeah, node calls a node destructor. Okay, so we can copy those. And then I need to use this iterate function. And here I cannot do the same thing I did in the linked list. This one has to be quite different. And I'm going to illustrate a concept called recursive functions for you. So a recursive function is a function that calls itself. Now you have to be really careful when you implement these, and there are two reasons for it. One is that you have to make sure that eventually the recursive structure ends. It needs to eventually go all the way back and return a value and finish. So you need to make sure that happens. And then the other thing you need to worry about is memory. So if you think about it, if I call this create node function, for instance, it has to allocate space for these variables. And if I call the create node function at the end of this, then it has to allocate space for all of these variables again and again and again. And it's going to just keep taking up more and more and more space until we hit the end of our control structure and it all collapses back and frees all of that memory. This can be quite intensive on the machine that's running it. So you need to be careful when you choose to implement a recursive function. And in this case, I know that I am implementing it over a search function that is roughly binary, or big O log n. And so I know that even if I have a billion records in this binary search tree, it's at most going to go 30 layers deep into my recursion. And 30 is quite a lot for a recursive structure, but it's not actually a lot. So we're fine here. And if I am doing something with a billion nodes in my binary search tree, I am probably doing it on a computer that is much bigger than this one. So this is going to be fine. So we're going to define an iterate function. So this is going to return a struct node pointer. It's called iterate. And this is going to be slightly different. So here we pass in the linked list itself, so our self variable. But this time, I'm actually going to pass in a node. So struct node pointer cursor. And then I'm going to need a few other variables. I wrote them down on my whiteboard, so I'm going to reference that quickly just to make sure that I remember it. Okay, we're going to pass in a compare function, or actually, in fact, I'm just going to pass in struct. I'm deviating from my script. That's a bit dangerous. Okay, struct binary search tree pointer tree. So we'll get our self, and that's how I'm going to access the compare function that I want to use. And then I need a void pointer for data. Finally, I need an int pointer called direction. And this is an interesting thing that I'm doing. Essentially, I want this function to return two values. So I want it to return the node pointer, but I also want it to return a direction. So should I be looking at the previous or the next value of this node? And I'm going to use my direction for that. You'll see that in a moment. So what we're going to do is say if compare, oh, no, not compare, because I'm passing in tree compare, and we're going to pass it cursor data, and then we're also going to pass it data. So we use our compare function, and if the result of that equals 1, then we know that it's next. Is that right? What is it not like? Has 1, expects 2. Compare is going to take what? Oh, I should not have put that there. Okay. Simple mistake. Okay. So if that equals 1, then I know that it's going to be returning a cursor, and the position that I should be looking at is this one. So let's do this example. Here's what I'm doing. Let's say I want to insert 15 into this list. Okay, it looks at 8, so cursor is 8. And it says, okay, well, we want something greater than. And that greater than is represented by our 1. So it goes to 10. 15 is still greater than 10, so that's our 1 again. So it goes here. 14. 15 is greater than 14, but there is nothing next to it. So 14 becomes the cursor, and our 1 tells us that the position we want is cursor.next instead of cursor.previous. So that's why I'm returning a 1 from the compare function. So we'll say return, well, actually what we want to do is set direction equals 1 and then return cursor. Okay, that is correct in a certain circumstance. Okay, check my reference. So what we want to do is see if the cursor has something next in that direction. So is this the end of the list? If we're trying to insert 15, let's say, what we want to do is say it's greater than 8, it's also greater than 10. Is there something already in the space that's greater than 10? If so, we want to do the same thing on that. Otherwise, we want to insert our node here. So here we actually want to check. So if cursor next, we're going to hit the iterate function again. So iterate, we're going to pass it tree, cursor, next, and data and direction. And eventually we want this to return. So here we're going to call the function again. and it's going to go through the same process again. And it'll just keep doing this until we hit our end statement. And it does not like this. I think I just spelled it wrong. I spelled it wrong up here, actually. And we'll just pass in most of the same variables, with the only difference being we're going to pass it cursor next. Otherwise, that's where we set direction equal to 1 and return cursor. And we can delete that here. Okay, another condition is that it equals -1. So if tree compare cursor data and data equals -1, we're going to do roughly the same thing. So if cursor previous, then we are going to say return iterate, and we'll pass it again, tree cursor previous data and direction. Otherwise, direction equals -1, and we are going to return the cursor. Okay, and the last position, so in any other circumstance, that is where you compare the two and they are equal, we are simply going to return the cursor, but we want to set direction equal to 0. And I need to put my dereferencing symbol in here. Okay, so this is a bit difficult to understand what's going on here. So let me first talk about this direction variable. I'm passing it a pointer to an integer, and this is called passing by reference rather than passing by value. So I'm passing in the memory address of this integer. So when I actually manipulate it here, it actually changes outside where I actually defined it. So this is how I'm essentially returning two values from a single function. Okay, so that's all that is. And I'm using these numbers 1, -1, and 0 to represent whether we want to look at the previous, the next, or the item itself. Now, the recursive structure is what's the strangest to understand. So let's go back to our example of inserting 15. Okay, so we're going to start calling our iterate function on the head. So our data, our first data, is going to have 8 in it. So we come down here and we use our compare function, whatever that may be, passing in 8 and whatever data the user is trying to insert. We do our comparison, and in this case, 8 is greater than the number that we want. So, well, let's just say this one is greater than. So 1 is when the second variable is greater than. I'll probably change that in the end, but let's just keep it for now. Okay, so if this one is, we're trying to insert 15, so 15 is greater than 8, so we return a 1 from that. And so we say the cursor's next is not null, basically. So we see that there's already a 10 here. Since there's a 10 here, we want to call the exact same function again, now passing in this node. So I didn't mean to do that. Let me move back to where I was. There we go. Okay, so now we call the same function, passing it the same tree, but now we pass it cursor next, so our 10. We pass it the data we're trying to insert or find or whatever, and our reference to direction. So now we come back up and we say if tree.compare cursor data, which is now 10 and 15, it's still going to equal 1. So we come back down here and we can see once again 10 has a next. Its next is not null. So we're going to call the function one more time, passing it again the tree cursor next, which is now 14, the data that we want to insert and the direction once more as a reference. We get to the function again, we compare 14 and 15, it's still going to equal 1, but now our next is null. There is no next for 14. So this is where we hit our else statement. We set direction equal to 1 because we want the next of our current cursor, not the previous. And we return the cursor. So that will come back to the outer iteration of this, and it will return the cursor, and it will just keep returning the cursor until we completely exit the iterate function, and we get the cursor itself, and we also get this value for direction out. Okay, so recursive functions are a bit tricky, but if you work through them like that, they make a lot of sense, and they can be a really elegant way to implement some features. Now again, remember that each time all of these variables have to be instantiated basically. So I'm creating multiple copies of them. But in this case, I'm only passing in pointers. So it's not really going to take up much memory space. And since it's using roughly a binary search, it's a billion nodes will not take up too much processing time or memory or anything like that. So we are good to go. This is going to be just fine. Okay, now I want my search and insert functions. So I'm going to define a search and an insert. So let's define them here. Let me pull up my header file just as a reference. And let's define, is this the right file? No, it isn't. I want binary search tree.h. Okay, so a void pointer called search, and we're going to pass a struct binary search tree pointer tree and void pointer data. And actually it's already defined there, so I don't need to have a prototype again. Let's just go down here. Okay, so void pointer search binary search tree pointer tree void pointer data. And here what we want to do is first get our cursor. So we're going to use our iterate function. So we're going to say struct node pointer cursor equals iterate, and we're going to pass it tree. We're going to pass it tree head to start, the data we want to look for, and a direction. Now I need to define this variable here. This is where I want it. So int direction, and this is going to be a pointer. So we can just pass it direction. And here what we want to do is it's going to iterate through the tree until it finds something with null or the thing itself. And what we want to do at the end is check, did it find the thing itself or did it find something that had no next or previous object? So what we want to do is say if the dereferenced direction equals 0, then we are going to return cursor data. Otherwise, we return null. So it's a tricky one. Like if we are looking for the number 15 again, what it'll do is it'll find 8, then it'll find 10, then it'll find 14, and it'll say, okay, 14 does not have a next, that's where our 15 would go. And so the result of the iterate function is this node for 14. But we're not searching for 14, we're searching for 15, and 15 is not in the list. So the direction in this case is going to be 1. So I can use that as an indicator that it didn't actually find what I was looking for. It found the adjacent node, and I'm looking for the specific node. So direction needs to be 0. Otherwise, it's not actually found the right thing. And that's our search function. So our void pointer for, what is this one going to be? Insert. And it's not a pointer return, it's no return. And it's going to take struct binary search tree pointer tree and void pointer data. And I'm noticing that my prototypes here are actually part of the struct, so I do want to copy them up here. So we'll say void pointer search, and tree. This is just so I can reference them anywhere in the document. You'll see why in a moment. Make sure that clears out. And in my actual constructor, I am going to say tree dot search equals search and tree dot insert equals insert. So my actual implementations of search or insert are down here at the bottom of the document, and I have my constructor up here. I would have to rearrange those if I wanted to do that, but since I'm using a function prototype, that's where it works, and that's why I'm putting those in there. Okay, so let's do our insert function. Again, we need a direction. And we're going to need to find the cursor. So struct node pointer cursor equals iterate. We'll pass it the tree. And we're going to pass it tree head. That'll give us the first node in the chain. We're going to be searching basically for data, and we'll pass it direction. And here all we need to do is insert the new node wherever the direction is pointing on the cursor. So if cursor, not cursor, but if direction equals 1, then we're inserting on the next. So cursor next equals, and how did I do this in the linked list? I think I just called the create node function. Is that right? Yes, that should work. I'll just pass it the data and the size of. So cursor next equals create node. We'll pass it data and size of data. Else if direction equals -1, cursor previous equals create node, passing it data and size of data. Okay. Now here's where Tim's suggestion may be a bit misleading. Okay, I need to do it a little bit different. When they are trying to insert something into the tree, I can't take the size of data because data is a void pointer. And if I take the size of the void pointer, it's giving me the size of the pointer, not the data stored at that memory address. So they're in the insert function going to have to return the size. And instead of calling that function here, they're going to call it outside. So when they actually call insert, that's where they'll take the size of the data they want. And I need to add that in here. Okay. And again, dereference these. And what's wrong there? Okay, it wants me to initialize it as null, which I'm fine with doing. Okay, and I believe that is all that we're going to want to do. Yes, so I'm going to just make a decision here that if the item is already in the tree, I am not going to do anything. So there will be no duplicate items. Let's take a look at our example. If I want to insert 14 into this tree, I'll see 8, I'll see 10, I'll see 14 is already there, so direction is going to equal 0, and it's just not going to do anything. It'll only insert new items in the tree, so no repetition allowed. And that is the basic use of our binary search tree. So when the user actually instantiates it, they are going to define their compare function themselves. They'll pass that into the constructor here, and then the rest will kind of take care of itself. And again, they'll be able to just worry about their data. They can simply pass in a reference to the tree that they're using and the data they want to insert, the size of their data, and it will just handle everything for them. And they can search to see where these things are. It'll return null if it's not in the tree, or it will return the actual data if it is in the tree. And that is basically how this will work. Now, it feels incomplete, doesn't it? It really feels incomplete. And the reason is I have not implemented a compare function. And what I'm going to do is next time I am going to use this to create a dictionary. And with my dictionary, I will create a compare function to pass in. So I'll be able to show you that. In the meantime, I'm actually probably going to write a few compare functions of my own for standard data types, int to int, character to character, string to string. Those are really easy to implement, and there's no reason I can't include them here. If I put them in this header file, then if the user wants to compare ints, they don't have to write anything. They can just pass it the function I already wrote. But that is all we are going to do on this today. I hope you really enjoyed the video, and I hope you learned something from it. If you are enjoying them, please leave a like on the video. It helps me grow my channel, and you can subscribe to the channel and hit the bell and all that good stuff. But really liking the video is very helpful for me, so I appreciate it if you do that. Anyway, I will see you next time, and toodaloo.